what we're going to do initially is work through test 1 of February of 2016, the 214 test from last year. For those, well, pretty much for all of you except for a few. The format is similar to the 213 tests. These tests are currently available on Blackboard, so you can download them and take a look at them. The test format is test 1 represents 15% of your total grade. Initially, the first time I ever taught it, it was 20, and then what I ended up discovering was that the first test is kind of a test that lets everybody know that I mean business and that physics is a real deal. So what I do is test 1 is worth less than test 2, which is worth less than test 3, which is worth less than the final. It just escalates, which means that I put a greater value on people who learn it over the course of the semester. If you learn it and by the final you know everything, you should be fine. Test 1 is out of 100 points. There will be 25 multiple choice for 2 points each. There will be 1 appetizer problem that will be 5 points. And there will be 3 problems for 15 points each, for a total of 100. It's called an appetizer problem. It's a problem to kind of just get your taste buds going and or your brain going, get a little start. It's a smaller problem, roughly 1/3 the size of the regular problems. Couple of things. One is with metaphysical certainty. And as I go through this, and this is kind of once again a reminder, if there is one thing that you study, make it the 2 review lectures preceding the test. I use it as a test platform for basically just writing the test. As an example, that final review session the day before the final for 213 in June, I basically took those notes, walked to my office, and wrote the test based on that. So yes, it's one of my weaknesses. So if you want to take advantage of it, feel free to do so. One of the problems will be a E-field vector addition problem. That is certain. It's one of the, it's critical, I think, to understanding what's going on. As we go through the other one that is a metaphysical certainty is REQ, I naught, and a voltage at a specific point. And we're gonna, when we go through the test, you'll see what I mean. Those 2 will be on the test. As for the rest, I could see RC circuit, C equivalent, particle motion, stuff like that. And what we're going to do today is we'll do the one from the spring. Tomorrow we'll do the one from, I think it's last summer, that particular test. And we'll do the multiple choice and we'll do all that fun stuff. The multiple choice, what I'm really going to do with these is they all come from a multiple choice bank. For test 1, it's about 50, 60 multiple choice questions. And so what I do is I just randomly pick stuff. And since it's the summer and time is so short, I'm not going to make any great additions of new problems. There may be problems or there may be multiple choice in here that I look at and go, that's just dumb, I'm going to rip that out. Or it's just badly worded, and I'm always proofing, but I don't think there's going to be a great number of new multiple choice, if at all. Format, first page of the test pretty much looks like a contract. Initially, if there was an individual who went and found every single one of my tests after I had taught it for 4 years, the first test, it was just a blank page with your name and student ID, and that was it. Now there's so much more, because what ends up happening is that I have to there's certain things that the students try to take advantage of. One is that they'll write the answers to their multiple choice on the page, and they'll take the they'll try to do the problems on the problem page itself, and that just makes it difficult for the grader. Bring a green Scantron. These are those narrow green ones with the 50 lines, and so bring that. And you can bring pens, pencils, markers, highlighters, a calculator, a ruler if you so wish. Don't bring notes, don't bring the book. If you do bring notes in the book, put it in your book bag. When you come in on Monday, before we start the test, all the book bags have to be up front or to the sides of the walls. If I find your cell phone on you during the test, that's a lot of points. So don't do it. Be sure to turn your cell phone off. Don't worry, I will have my cell phone on in the event of a tornado attack or mutant invasion, or if it did happen, I'd be so happy. If it was a zombie apocalypse, I'd know about it, and then we'd cancel the rest of the semester. So don't worry about it. So let's get started. The test, you're not allowed to bring in an equation sheet or a note sheet for the test. I provide you with equations. How you use them is your business. And we'll go through this, constants and all that fun stuff. So let's briefly go through all the multiple choice. It's 25 of them, shouldn't be that hard. 1 ampere is what? Coulomb per second. Yes, and just shout it out. A negative particle moves from left to right. It slows down, which means it's feeling an acceleration in that direction. What is the direction of the E field? It goes from left to right. Negative charges feel force in the opposite direction, or accelerations in the opposite direction of the E field. Yes?
What version is it?
Oh, a good question. I would probably say it was the first version. I would say that it's number 58. So you rub silk on a glass rod, which is false. We went over this in the first lecture, so those electrostatic problems are going to be in play. 2 resistors are in series. Which of the following is true? They're in series. It's C. If they're in series, the current flowing through the first one has to be the same as the current flowing through the second one. Now, for this one, what we're doing, what typically happens, and for the ones who took 213 in the regular semester, we move very quickly. And so with the first 3 days, we're just covering everything left and right. Days like this, we fill in the gaps. The potential difference across a capacitor doubles. The electric field between the plates does what? It doubles. Now, what we'll do, so Q is equal to CV, and V is equal to ED. So for a capacitor plate, the potential difference is related directly proportional to the electric field. So this is the one that we're going to look at. The potential difference doubles, so the electric field must double as well. There's no square root, there's no square, there's nothing like that in there. The potential at ground is what? D, 0. Ground is our reference point. That's the point where we go, that's 0. Now, in Brevard Hall, you let go of a positive particle that has a mass of 3 grams. It sits there. It moves nowhere. In which direction is the electric field? It's from floor to ceiling. Because the force from the electric field has to be up to balance the force of gravity. Because it's not moving anywhere, you know that it's in translational equilibrium, which means the sum of the forces is equal to 0. So you know you're in Brevard Hall, that's on the planet Earth. Okay, fine, I'll change it to Lewis. Which means there's a force pulling down due to gravity, so there has to be a force up. It's a positive particle, so the E field must be up. The ground is attached to the negative lead of a 15-volt battery. What is the potential at the positive lead? It'd be B. So if you have something like this, that means the potential there is 0, so the other side must be 15. There is a multiple choice out there, it may be in this, where I attach the ground to the positive lead of the battery. So if I put the ground on the positive lead of the same battery, what would be the potential on the other side of the battery? Negative 15. The unit for charge is what? Coulomb. You charge the electroscope by induction. What actually touches the electroscope? Finger. B. You bring the rod close to the ball. That induces, or that redistributes charge. Touching the finger pulls charge off or puts charge on. 11. I like 11. Which the potential difference across a resistor is 0. Which of the following is true? D. I, you could say, is V high minus V low over R. If both of those potentials are the same, like in the multiple choice problem, 0 divided by R is 0. So there is no current flowing through the resistor. You have 2 resistors in parallel. The current flowing across R1 doubles. R1 and R2 are constant. The current across R2 does what? So let's talk about this for a moment. So we have 2 resistors, R1 and R2. And so there is a current there and a current there. If I1 current increases, What do we know about the potential difference across R1? Does the potential difference across R1 goes up or down? It goes up. Once again, V high over V low. So if I increases and R is constant, the potential difference across that resistor must go up. So if that potential difference goes up, what happens to the potential difference across R2? Does it remain the same, go down, or go up? It goes up. How do we know this? The potential difference across parallel resistors are come on, give it to me. Are what? They're identical, correct. Now, just as a word of advice for those of you who are going into medical school, when the surgeon, doctor, and everyone asks questions, they're going to want answers quickly and confidently. I'm just a small physics professor. Wait until you deal with your surgery room hygienist. He's going to want answers fast and confidently. So if the potential difference across R2 goes up and R2 remains the same, what must happen to I2? It goes up as well. So really what effectively happened, in order to get the current flowing through R1 to increase, you had to increase the potential difference across the circuit, which means I2 has to increase as well. So you have two capacitors in series, C1 and C2. The value of C1 doubles, C2 does not. The equivalent capacitance does what? Now with this, I'm willing to admit, what I end up doing, how I did this, when I first dealt with it, I was like, I don't know. But let's say that C1 was 2 farads and C2 was 4 farads. So the initial C equivalent is 1/2 plus 1/4 inverted, which means it is 4/3 farads. So now let's say that C1 doubles, which now makes it 4. So this is now 1/4 plus 1/4 inverted, which makes it 2. So it goes up. So what I do is I just mathematically just ram it through and just prove it. What there ends up having, there are two, I don't think it's in this test. There are two problems about capacitors. One where it's in series and C1 doubles, and the other one where they're in parallel and C1 doubles. You have two capacitors in parallel. C1 doubles. What happens to the equivalent resistance? Goes up, goes down, remains the same. What do you do with capacitors that are in parallel to get the equivalent capacitance? Yeah, exactly. So you just add them together. So if it's 2 plus 4 is your first, or 6, now you've got 4 and 4, now you've got 8. So really the short answer is, for both of these equations, capacitors in series or in parallel, if one of the capacitors increases, the equivalent capacitance increases as well, for both series and in parallel. Two resistors are in parallel. Which of the following is true? Now you get to say the right answer. or U? Either one. Or in, huh? You sum them up, correct. Which ones? 1 and 2, 1 and equivalent, or 2 and equivalent? 1 and 2, yes. And granted, you had the exact small tone of insolence that I appreciate from my students when I'm asking dumb questions. You don't want to be completely rude about it, but you go, really? You just add them up, 1 and 2, big deal. Which of the following can only be positive? What did I go on and on about in lecture? The electric field. You will never get a negative electric field value. If it's an electric field vector, you can have components that are negative, but the actual magnitude is always positive. Multiple choice like this, we're not going to have. I'll yank that stuff out because conversions will happen in the test. But which one is 2 nanometers? D. A positive particle moves from left to right. It accelerates in that direction. What is the direction of the E field? It's E, left to right. Positive particles accelerate in the same direction as the E field. Which of the following is not true? Answer is not C. So which of these cannot be a vector? Potential. You charge the electroscope by conduction. What actually touches the electroscope? The rod. The object is doing nothing. Which best describes this? E. You rub rabbit fur on an ebonite rod. What is true? Actually, are you sure it's B? Oh, you said E. You know what? One of the things I would, if I went back and changed the alphabet, I wouldn't make B, C, D, and E all have the same like vowel sound at the end of it, the same E. Oh, and this is the other one. Ground is attached to the positive lead of a 15-volt battery. What is the potential of the negative lead? A. Stuff like this I'll probably yank out because it will be used heavily in problem 1. 4 meters at 90 degrees is what? C. Which of the following can be positive or negative? Well, yeah, it can be. Mine can be positive or negative at times. But what other thing can be positive or negative? E, potential. Force from Coulomb's law has to be positive. Electric field has to be positive. Explode and C are both just dumb answers. Current is plotted on a graph as a function of potential difference. The slope of the graph is what? Covered it yesterday. A, yes. Inverse of resistance. So that is the multiple choice. Now there are other versions of this running around. And so you can work on that. Now what we're going to do is run through these problems, and then I'm going to start talking about ideal and non-ideal voltmeters and ammeters, since that would have been helpful yesterday. All right, first problem we're gonna do. The equivalent of the capacitance of this circuit is 58 microfarads. What is the value of H? So you have all these capacitors. They're all these weird angles. Lesson that we learned for both resistors and for capacitors. The lines don't really mean anything. Look at this, it all just goes crazy. First thing I like to do when I'm given a, I should show, for someone's birthday party, they had just taken my course and their boyfriend drew a sample problem such as this, but it had like 100 different resistors and it all spelled out her name, and so she wanted to know what her equivalent resistance was, and it was just obscene. There were just wires going everywhere. So the first thing you really want to do with a problem that looks like this is just straighten the thing out. Make it go into boxes and stuff. As long as you physically don't move any of the wires, with relationship to any of the capacitors, it's a legitimate move. And so the first thing I do is just straighten the dang thing out. And then what I look for are boxes where I know I can smoosh capacitors together. And there are actually two that are available. There is that box, and then there is this box. It doesn't matter if it's resistors or capacitors. This technique is identical. So I have, I'm going to call this box A, and I'll call this box B. So A is 1 over H plus 1 over 3H inverted.
What happened to the H in the middle of the box?
Oh, I forgot that one. All right, hold on. And it doesn't affect anything because it's just sitting there in the middle. I can't draw a box around that one. Those two are still the boxes. And thank you. B is 1 over 2H plus 1 over 5H inverted. So the common factor is 3H or 10H. This is 3H. 3 plus 1 is 4. So it's 4 over 3H inverted, or 3/4 H for A. For block B, its equivalent capacitance, 10H, so this is 5 plus 2, or 7 over 10H inverted. And this becomes 10/7 H. Now what I have is a 2H with a 3/4 H, an H, and a 10/7 H. And then the box that I draw now to squoosh is that box. Because what I have are 3 capacitors in parallel. And I'll call that box C. Now C is equal to 3/4 H plus H plus 10/7 H, which gives me and it's kind of a weird number 89/28H. And it's critical to keep that value as a fraction. If you start plugging and chugging and starting to round stuff off, you're going to clip information that will be useful. Because the thing about this is, I wrote 58 microfarads as the answer or the equivalent capacitance for this thing. That's an odd number. Not like 10 or 20. 58. What does that mean? Well, now I have a 2H and a 89/28H in series. So we have to do the series capacitor. So C equivalent is equal to 1/2H plus 28/89H invert. And that gives me
Why did you flip it? Why did you put 28 on top and then?
because effectively I'm taking, or did you just answer your own question?
Yeah.
Okay. And to the rest of the group who don't understand what I did, the equivalent is 1/C1 plus 1/C2. C1 is 2H, so there's this 2H down there. C2 is this, but when you put that in the denominator, the 28 pops up to the numerator. And it becomes this ghastly, oh wait, I haven't inverted. Did I invert? Okay, no. No, not that. It's 178/145 farads is equal to C equivalent, which is equal to 58 microfarads. So the equivalent, or the value of F, is 58 times 145 divided by 178. Please, by any miracle, make this work. 58 times 145 divided by 178. And I don't think I made it nice. So it's just 47.2 farads. That's a weird. Let's look at the math real quick. That's right. Huh? That's what I got on the study guide? Excellent. All right. Okay, then I'm wrong. So there. What I try to do, if I have enough time, I'll actually try to get the numbers to work out whole. 58 microfarads makes me think that it did. Probably what happened was there are three versions. The 58 microfarad didn't produce a good number, but what may have happened is I may have changed things, like make that value like 178, and then stuff would cancel out and do all sorts of. And in fact, this is not farads, it's microfarads. So it's just a simple C equivalent. Yes?
Will you explain again why you flipped that? Flip the 28 over 25. Did you just go ahead and flip it?
Well, C2, or this one right here, that C2 is 28 over, I'm sorry, it's 89/28H. And I needed to get it into the form of C2. So that's 1/89H/28. that 28's in the denominator of the denominator. So it can become 28 over 89.8, 89H. And now, problem 1, electric field addition. There are two charges. On one of the problem sets, that charge vector addition is just a bear. It's just evil. But for this one, I promise it's going to be a lot more, it's going to be a lot easier in terms of what you need to do. In the first one, you've got two charges. I draw these charges out. Grid at -2, 5, there is a -2 microcoulomb charge. At 4, 0, there is a +3 microcoulomb charge. And I'm looking for the E field vector at -2, 2. What is the electric field at that point due to the two charges? First thing I do is I draw the electric field lines from each of these charges. Negative charge means that the E field is radiating inward from that point, which means that E1 is going due north. This thing is a pure positive Y vector. It is an instant conversion vector. It is not a vector that's difficult in terms of finding its component notation. The positive one it repulses. So this is the line connecting the two, and it continues like that. So that's E2. So if we're going to draw, now I'm not sure of the magnitudes, but the one thing that I do kind of know is this total E field vector. If I had to put money on it, is going to go up and to the left, is my best guess. The first stage is to find out the magnitude of each of these charges. E field. E1 K Q1 over R1 squared, and E2 is K Q2 over R2 squared. R1 is the distance from there to there. R2 is the distance from there to there. That's the first thing I need. So K is 9 times 10 to the 9th. Q1 is 2 times 10 to the -6. R1 is from there to there, -2 to +5. That's 7 millimeters. Or 7 times 10 to the -3 squared. So this gives me 18 times 10 to the 3. 9 minus 6 is 3. 9 times 2 is 18. Divided by 7e-3 squared. And I get a big stinking number, which I will write out as 3.673 times 10, 8 newtons per coulomb. Now E2, K is 9 times 10 to the 9th. Q2 is 3 times 10 to the negative 6. R2, the change in X, we go from negative 2 to 4, so that's 6. That change in distance is from negative 2 to 0, so 2. So R2 is equal to square root of 2 squared plus 6 squared. 36 plus 4 is 40. So the square root of 40. And actually, this is one of the interesting things. So this is 6.324, but R2 squared is 40. What am I looking for down here? I'm looking for R2 squared. Not R2, R2 squared. So I know that R2 squared is 40, so I just put 40 down there. It's the same thing as 6.324 squared. This makes this 27 x times 10 to the 3 divided by 40. And what am I doing wrong right now? And I forgot. Well, first, you're wrong for one reason, I'm wrong for another reason, and actually in this particular case, let's work through this both. Your question is, where's the negative charge? Why isn't Q1 and E1 negative? Who's the one who said that? Why is the charge, hold on, what charge are we talking about?
I was just talking about multiplying it by 10 to the negative 3. Because you just said square root and then you square it and then it cancels out.
Yeah, I'm really forgetting the same rule that I've told everybody else. Convert, and it's the best thing to do, convert this thing to millimeters. And let's just work this out now. R2, 2 times 10 to the negative 3 squared plus 6 times 10 to the negative 3 squared. If the units were just straight up meters, this would not be a problem. Well, what I did right here, and I'm going to back out of that. I'm going to find R2 in meters. So the 2 millimeters is 2 times 10 to the negative 3. The 6 is 6 times 10 to the negative 3. This one was easy because it was just 7 millimeters, and I just converted it to 7 times 10 to the negative 3. Let's find out. Right now, I'm not so sure, so I'm playing safe. And you're right. So my new R2 squared is 4 times 10 to the negative 5th. Or if you square root that, R2 is 6.324 millimeters. So really, this number should be 4 times 10 to the negative 5th. in a way, this is kind of a demonstration of why probably the best thing you should do is convert everything into meters, seconds, kilograms, all your base units first. Don't use millicoulomb, don't use millimeter. Just straight up convert it to meters, and then you can't go wrong from there. Because the thing that I noticed with that 40 is that I was going to get a radically different number than the other charge, than the other E field, and I knew that was bad news. And I get 6.75 exact times 10 to the 8th newtons per coulomb. Now with E1 is an instant conversion vector. I know for a fact that that E field is due north. So E1 is 0x hat plus 3.673 times 10 to the 8th y hat. E2 is a little bit more tricky. There's the charge, there's the point. To figure out this reference angle that I need, I know that that distance is effectively 2 and that is 6. The fact that they're in millimeters or in meters doesn't really matter for what I need it. That angle there, which is going to be my reference angle, is that angle there. And if that's 2, and if that, and actually, that angle there and that angle there is the same as that angle there. Because these are two parallel lines with a bisecting line. That theta r is inverse tan of opposite, which is 2, over adjacent, which is 6. So that reference angle is 18.43 degrees. So now, at that point, with that vector and that reference angle, E2x is E2 cosine theta r, and E2y is E2 sine theta r. E2 is 6.75 times 10 to the 8th cosine of 18.43, 6.75 times 10 to the 8th sine of 18.43. And I get 6.40 times, well, 6.404 times 10 to the 8th. This gives me 2.134 times 10 to the 8th newtons per coulomb. So really we had the more complex front end. The first thing you had to do was, oh my goodness, I got to find the E fields for these things. Thank goodness Dr. Eschenberg was nice and gave me an instant conversion vector for E1. E2 got a little bit sloppy, but all you have to do is you have to find the reference angle first, and if you've got the reference angle and the magnitude, you can go then and break down the vectors. Remember the 3 steps of vectors. Break them, add them, recombine. What we have done is extended the first portion, the break them down portion, with the extra layer of getting your E fields determined. Now E2, by physically looking at it, E2 goes down into the left. Vectors do not care about their location. This vector could be over here, here, or there, but that vector is going down into the left, so its X and Y components are both going to be 0. So this becomes negative 6.404 times 10 to the 8th x hat minus 2.134 times 10 to the 8th y hat, and we're ready to add. Well, the first part is easy. Negative 6.404 times 10 to the 8th x hat. This will be a plus 3.673 minus 2.134. I get positive 1.539 times 10 to the 8th y hat. And that is the electric field vector in component notation. That's the sum. We've done step 1 and 2. Step 1 is this getting to this and setting up that. Step 2 is just adding them together, x's to x's, y's to y's. Now remember at the beginning we kind of visually drew this thing out, and what did we know? That the E field is a second quadrant vector, physically located in the third. We don't care about locations. It was going up and to the left, which means the vector should have a negative x and a positive y. Quick question. Its absolute angle should be between what angles? 180. Hold on, what did you say? 90 and 180. Up and to the left. It's not pure vertical, so it's got to be greater than 90. It's not pure horizontal, so it's got to be less than 180. So our final E vector looks like that. And so we draw again. Now remember, when you look at this and compare a lot of the parts to the vector addition problem from vector addition problems from 213, now it's the same thing, weirder numbers, but that's my E magnitude, and it is the square root of 6.404 times 10 to the 8th quantity squared plus 1.539 times 10 to the 8th quantity squared. And that gives me a total the numbers are just bigger, it's just no big deal. Gives me a square root answer of 6.59 times 10 to the 8th newtons per coulomb. The parts are still the same. The last part, the part that once we're done with the problem, is this. We have, this is our EY, this is our EX. We're dealing with the magnitudes only. That is theta R, so theta R is inverse tan of EY mag over EX mag. When we're adding vectors in the way that we do it, when you're dealing with sine and cosine, you never plug in negative numbers into those functions. What we do is we use logic and reason to determine the signs. So this becomes tan -1. Now both of these are 10 to the 8th. So those 10 to the 8ths will cancel. So I can just get away with writing 1.539 and 6.408. I don't have to write the rest of it. It's irrelevant. It cancels anyway. And I get 13.5 degrees. And that's the reference angle. A reference angle for the second quadrant. How do I get the absolute value for a second quadrant reference angle? 180 minus, exactly. So that's 166.5. Okay. So the answer is 6.59 times 10 to the 8th newtons per coulomb at 166.5 degrees. Yes, the problem is way more tedious than what you're used to for a vector addition problem. The thing that it does is it combines vector addition, which is something that you learned in 213 thoroughly, and adds on the front end determining E-field vectors. So we're adding determining the E-field vectors in front of a vector addition problem, which makes it a fair problem on the test. This is going to be on the test. The other advantage that you have looking for is I write the tests for an hour 15. You guys will have 2 hours, so you can take your time with this kind of stuff. Now for problem 2, given the capacitor shown below, determine the values listed in the box. I want to know the value of C. At time 0, I have an unknown max Q. I don't know what that max Q is. At time 10 seconds, it's 2 coulombs. At 20 seconds, it's 0.4 coulombs. We are discharging. In an RC circuit that's discharging, and really this is not correctly drawn. Really what it should happen is like a short in the line with a switch or something. I mean, for an RC circuit, you don't really need the diagram. But what you do need is that V is equal to V max e to the negative t over tau. And initially when I looked at this, just 30 seconds ago, I looked at this and go, what was I thinking? But let me show you what's going on. If you have Q equals CV as the relationship between charge and capacitance and potential difference, you could say that Q over C is equal to V. So this becomes Q over C is equal to Q max over C e to the negative t over tau. The two capacitance cancel, and I'm left with Q equals Qm e to the negative t over tau. And so that's how you can get the charge equation for a discharging capacitor. Now, one of the things that I specifically said is you do not know the maximum charge. However, you do know that at Q1, that's true. And at Q2, you have Qm e to the negative t2 over tau. So you've got these two equations. Within tau, there is a C that we don't know. So we don't know that C, we don't know that C, and I don't know what those Qm's are. And when I wrote this, I wrote it with the intention of sometimes you got to push boundaries a little bit, and I wanted the student to recognize this is eerily similar to a problem I did in 213. Which problem is it? And it had to deal with sound. And it had to deal with a roulette wheel. Remember how we took the sound, the frequency that you heard coming and going, and I specifically said you don't know the source frequency? What did you do? You divided one by the other. There's nothing wrong with that. So what I did is Q1 divided by Q2 is equal to Qm e to the negative t over tau, or T1 over tau, Qm e to the negative t2 over tau. Qm's cancel, it's an unknown, or it's an unnecessary unknown. So now let's do some mathematics. Q1 over Q1 over Q2, I've got those. E to the negative t over tau, T1 over tau, e to the positive T2 over tau. Bringing an exponential up from numerator to, or from denominator to numerator, you flip the sign in the whatever power it is, and so you get this. This will give me e to the t2 over tau minus t1 over tau. When you've got two exponentials multiplied by each other, you can just add the powers. We attack it with natural log. Which now gives me natural log Q1, Q2 equals T2 over tau minus T1 over tau. Multiply both sides by tau. Tau ln Q1 over Q2 T2 minus T1. Now tau is equal to RC. I'm solving, what am I solving for anyway? I'm solving for C. So C is equal to T2 minus T1 over RLN Q1 over Q2. I have T2 and T1. I have Q1 and Q2. I have natural logs, or I have what natural logs are, and I got R. Plug and chug. You may now plug and chug. T2, 20 minus 10. R is 4 mega ohms, 4 times 10 to the 6th. Natural log of Q1 2 over Q2 0.4. And that gives me 1.55 times 10 to the negative 6 farads. And so you've got that. And so that's this problem. The really tricky thing, and this is one of the things, it makes me so happy when people say this. It only makes me stronger, probably allows me to live a little bit longer, are people who tell me the problems are impossible. When I get to a test, I've done the problem already. Typically the hour before the test, I'll sit and work through it. If it doesn't happen to work, then like there was one time in 213, there was a problem that didn't work quite right. So I had to make a change real fast. The trick was this right here. And that's the fun part. I would say, looking at this, if I had to, I'm looking at this test and I go, what would I do differently about this? I love this. This is going to be on it. I love this. We're about to do this. I love RC circuits and charging and discharging. We're going to do this. The one that sticks out like a sore thumb is this guy, the equivalent capacitor, because we're doing equivalent resistance down here. So I'm not happy with it. What could be, I'd have to look at that other test. But the thing that I'm thinking about, problem set 2, the capacitor problem where a particle moves and you got to find the velocity, or if you've got the big charge and a little charge like that, what's the distance d when it comes to a stop? And we'll talk about that. We can talk about that either tomorrow after sometime, or sometime later in this class. But I'm not fond of that right now, because I think this covers it, everything that I really need to cover. The last problem, the problem that's going to be on the test, is this. You've got a circuit, and I ask the 3 main questions, REQ, I naught, and VA. I pick a point in the middle of the circuit, and I go, give me the potential at that point. And of course, for all of these, the ground is going to be at the base of the base of this thing. So what you do is a lot like this. You draw out the resistors, and you draw it in a way that's a little bit more coherent. R1, R2, R3, R4, R5. And that's all I really draw at the moment. And then you start looking for places where you can squoosh stuff. The 2 boxes here, R1 and R2, can get squooshed the two boxes down here, R3 and R4, can get squished. So that now, I mean, I'm not even going to deal with numbers for the moment. So this is R1, 2. This is R3, 4. And this is a pen that must be thrown away. And this is R5. So the next squish box I'm looking for are these two guys, R1, 2 and R3, 4. And they combine to give me R1, 2, 3, 4 and R5. And really what you guys need to do is pay attention to how things are squished. And in the order that they're squishing. And so R1, 2, 3, 4, and R5 gets squished down into REQ. That's the first thing I do, is I just squish everything down graphically and just take a look at it. Well, the first two boxes are just series resistors. You add them together. R1, 2 is R1 plus R2, which makes it 10 plus 20, which is 30 ohms. Now, in the middle of a problem, I don't give a rip about units. It's the answers at the final that I do care about. R3, 4 is the sum. 3 is 30, 4 is 40, so that makes this 70. The next thing I do is I know R1, 2 and R3, 4 are in parallel. So R1, 2, 3, 4 is equal to 1 over R1, 2 plus 1 over R3, 4 inverted. Now this is where you have to keep things in fractions. So this is 1 over 30 plus 1 over 70. It does not equal 1 over 100. But what happens is, really? I must have planned ahead. Oh, I did plan ahead. Good for me. 1 over 30 plus 1 over 70 inverted is 21. Dun, dun, dun. It's like I was planning ahead. The last part you simply sum up. REQ, R1, 2, 3, 4 plus R5. So this is 21 plus 5, or answer 26 ohms exact. Now I was being a jerk and used potential that is not, I wish it was a multiple of 26, but it's not. So there'll be a small fraction. The first step, write out graphically how you squish things. The next step, get REQ from looking at those diagrams. So the first answer has been done, REQ. The second answer, I naught, is trivial. Take the battery, divide by REQ. 100 divided by 26. And you get just some freak current. 50 divided by 13 amps. The answer that I would accept, you're going to use this for the rest of the problem, but the answer that I want is 3.85 amps. And that is the base current. Now comes the tricky part. VA. I know from all my resistances that this end is 100 volts. And I know for a fact that this end is 0 volts because that's the end connecting to the ground. There's a whole lot of information that I don't have that would be quite helpful. So what I got to do is I've got to use this equation that I've mentioned before. I equals V high minus V low over R. That the current going through any resistor is the difference between the potentials divided by resistance. You can only answer one of the values if you have the other three. If you only have two, you can't answer it just then. I can't figure out the potential here because I don't know the current going through that upper band. I know the potential there, but I don't know the resistance, or I don't know the current flowing through that resistor. The thing that I can figure out, and so this is how, through experience, you start looking for regions where you know you can figure stuff out. I can figure out the potential right there. And I'm going to call that VB. Because I don't know VB, but I do know V low. That's 0. And I know the current going through R5. All the current going through the circuit has to go through R5, so the current going through R5 is I naught. So solve for V high. IR equals V high minus V low, so IR plus V low is equal to V high. That's 0. So V high, which is RVB, is equal to the current, which is 50/13 times the resistance, and R5 is 5. So 250 over 13, which is a horrible number. So it's the lowest common denominator I can get is 250 over 13. And that's the voltage. Once again, when we're working towards our final answer, you do not shave information off anywhere. That's the potential here. Now, really what I'm going to do is I'm going to explain it here. I know the potential there is 100. I know the potential there is 250/13. Remember when I said when you sketch these things down to their equivalent resistance, keep track of the intermediate pictures. Because in this particular case, I know what R12 is. It's 30 ohms. I know V high. I know V low. So I know what I12 is. I know the high and I know the low. I know the current in between. So the current in between is 100 minus 250/13 divided by R12, which is 30. So the current I get is 35/13 amp. That's the current flowing through R12. And what do we know about series resistors and their currents? That the current flowing through R2 is blank with respect to R1 for series resistors? They're the same. So I12 is I2 and it's I1. I now have the current flowing through R1. And if I know R1, I was given that. I know V high, I was given that. I know R1, I can get V low right now. So solve for V low. IR, V high minus V low. So V low is equal to V high minus IR. The V high is 100. The I is I1, which is 35/13. The R1 is 10. So the V low, or VA, is 73.1 volts. And so that's the final answer. There is a very rigid structure to find REQ and I naught. Finding VA is going to be a little bit of a freestyle. It's the way that I look at it, it's an equivalent of a Sudoku puzzle. What do? You look for the spots where it obviously, that square has a 6, it has to. That square has a 4, it must. And the more squares you put in, the more that you can solve. It's the same thing for the circuit. So, now granted, me going through it did take almost an hour and a half, but it was me slowly explaining this stuff and pointing the parts out along the way. So that is test 1. And before I forget, I'm very bad at stealing these things. I know. Let me return it to you right now. All right, next. So very brief, what we're going to do today for the rest of the class is we're going to go over, I was debating during the class yesterday, should I talk about ideal ammeters and ideal voltmeters and blah, blah, blah. And I was like, we've talked about series and parallel. That'll be good enough for a functional understanding. Now I'm going to fill in the details. Voltmeters and ammeters measure quantities about the circuit. I'm not sure if the certain values within the circuit. These devices must not affect the circuit or at the very least affect it minimally. So voltmeters and ammeters are pieces of laboratory equipment, and laboratory equipment study the experiment that you've designed or put together. They do not, should not, must not affect the experiment. You don't want these things changing the behavior of the circuit. Voltmeters and ammeters are electrical circuits on their own right. Using them with electrical circuits can affect the other circuits. So there has to be certain things that these tools must have in order to minimize the effect. There is the ideal, and then there is the non-ideal. The ideal is the perfect world. Or we can think of it as like whiteboard, or in this case, paper physics. Non-ideal is the real world. And it is your lab. Your lab is a non-ideal world. Those voltmeters and ammeters are non-ideal. The voltmeters and ammeters that I use in this lecture are ideal. A voltmeter a circuit we can just think of as a resistor. The voltmeter, what was the one thing that you did with a voltmeter? Is that you put that voltmeter, one lead on one side of the resistor, the other lead on the other side of the resistor, so that you could measure the potential difference across that resistor. The voltmeter is in parallel. The ammeter that's the circuit, that's the ammeter. They have to be in series. Now you can think of the voltmeter and the ammeter having a little resistor inside it. So the equivalent resistance of this voltmeter and circuit is 1 over R plus 1 over RV inverted. 1 over our REQ for the ammeter is 1 over R plus 1, no, bad professor. R plus RA, because it's in series. So in a perfect world, let's look at the ammeter because it's the easiest one. In a perfect world where the ammeter does not affect the equivalent resistance at all, what is RA? 0. So in a ideal, the RA is 0. Now we don't live in an ideal world, so we live in a non-ideal world. So if we can't get 0, we must get numbers as close as we can to 0. So because of the specific components that go into an ammeter, you want that ammeter to be, you want RA to be a lot less than R. And so typically when you have resistors in the hundreds and 200s and 300s, you want that equivalent or the resistance of your ammeter to be in the 10 to 30 ohm range. That's typically how they do it. So this ammeter isn't really good in measuring currents flowing through like 5 ohm resistors. That's why we typically give you 100, 200, 300 ohm resistors. Because a 300 ohm plus 10 ohm resistor will give you 310. That's not that big of a deal. But if you put a 30 ohm ammeter in series with a 5 ohm resistor, it is going to affect the behavior of the circuit, because now the circuit's gone from 5 to 35 ohms. Things will mess up. Now for the voltmeter, you don't want the voltmeter to affect the circuit. So in an ideal world, we want the equivalent resistance to be R. In an ideal voltmeter world, what is the perfect resistance of a voltmeter? Now, let's observe your answer and show you why it's horrendously wrong. It should be infinity. If RV was 0, that number there would be infinity. If that number there was infinity, anything plus infinity is more infinity. Infinity inverted becomes 0, and the equivalent resistance is 0, not R. So effectively what you've done is you've blown up the world. Congratulations. But if RV was infinite, in an ideal world, one over R plus 1 over infinity inverted is 1 over R plus 0 inverted, which is 1 over R inverted, which is R. So in an ideal world, you have resistances that are infinite so that it doesn't affect the circuit. In a non-ideal world, if it can't be infinite, it's gotta be huge. You're looking for a resistance of the voltage which is much bigger than the resistors that you're using. So if you use 100 ohms, thousands ohms, 10,000 ohms resistors, your voltmeter's gotta be in the mega ohm range. So typically, RV is on the order of like 10 to 30 mega ohms. Because let's say your resistor was 1,000 ohms. 1 over 1,000 plus 1 over 30 times 10 to the 6th. If you actually did the math, it'd be fairly close to 1,000 and doesn't really affect anything. So you want ideal or non-ideal voltmeters to be on the order of mega ohms, and you want your non-ideal ammeters to be on the order of like a couple tens of ohms. So in the there was a question. So you have a non-ideal voltmeter. The resistance of the voltmeter can either be 0 ohms, 10 ohms, 1 mega ohm, or infinite ohms. What is the resistance of a non-ideal voltmeter? Which answer would you pick? Now the two that are impossible are 0 and infinity. 0, you're dealing with, that's a resistance of an ideal ammeter, and infinity is the resistance of an ideal voltmeter. We're dealing with non-ideal. So that leaves us with 10 or 1 mega ohm. So which one is the resistance of a non-ideal voltmeter? 1 mega ohm. There were people who argued that 10 ohms could be the resistance of a non-ideal voltmeter. My response is, I'm looking for a functional non-ideal voltmeter, not a really cruddy non-ideal voltmeter. If you had a voltmeter with only 10 ohms, it would just be horrible. But a voltmeter of 1 mega ohm is a realistic resistance for a voltmeter. And so that's the answer. Something like that could crop up in the multiple choice. The last thing I'm going to do is, now really all I was kind of doing, the thing that I kind of taught yesterday, voltmeters are in parallel. Once they told you voltmeters are in parallel, you should probably poke around with this. And ammeters are in series, you poke around with that and then you kind of figure it out. But this is the detailed explanation as to why we do what we do. Could it end up on the exam today? I don't know. I don't talk to the TAs. The last thing is, and actually, I'm going to take this off. What I'm going to do is an RC circuit where the resistance is 5 mega ohms and my capacitance is 2 microfarads. So by just giving those numbers, what's my time?